So we start off with the expression for n, which was C alpha integral d epsa g epsa over z inverse e to the power x minus, e to the power beta epsa minus 1. And we know how to convert this because this g epsa goes as epsa to the power alpha minus 1. So d of beta epsilon times beta epsilon raised to the power alpha minus 1 divided by z inverse e to the power beta epsilon minus 1 divided by beta to the power alpha. Now this is a repetitive statement, but it is just to ensure that if you have forgotten, you can start off from the scratch. So C alpha beta alpha, and then you see that this integral is now 0 to infinity, 0 to infinity, 0 to infinity dx x to the power alpha minus 1 z inverse e to the power x minus 1. So that this gives me C alpha over beta alpha, and I need gamma alpha divided by gamma alpha because I need a alpha minus 1 factorial to relate it to the Bose integrals that we have defined. Dx x to the power alpha minus 1 z inverse e to the power x minus 1. And this is C alpha over beta alpha times gamma alpha f plus alpha of z. Now I want to take a derivative with respect to temperature, chemical potential being held constant, but this also has to be evaluated very close to Tc. So to make my life simple, one can simply say that, look, I can replace Tc everywhere, but then my derivative is going to be identically 0. So what we will do is we'll replace this by saying that I have z equal to 1, so that del n del t is going to be del t of C alpha gamma alpha raised to the power beta alpha f alpha plus 1 evaluated at z equal to 1, extremely close to Tc, and this becomes del t of C alpha gamma alpha raised to the power beta, divided by beta raised to the power alpha, and then I have zeta of alpha, the Riemann zeta value. This quantity then becomes C alpha gamma alpha times zeta of alpha, and then I have derivative of del t of 1 over beta raised to the power alpha, which is C alpha gamma alpha zeta of alpha del beta of 1 over beta to the power alpha times del beta del t. This is zeta alpha. Now del beta del alpha is del beta of beta to the power minus alpha is minus alpha beta to the power minus alpha plus 1, and del beta del t is going to be del t of 1 over kbt, which is going to be minus 1 over kb t square, and which I can write as minus 1 over kbt times 1 over t, so that this becomes minus beta over t. So I have minus alpha beta raised to the power alpha plus 1 times minus beta divided by t, and you see that one factor of beta cancels with this one factor sitting over here, and the two negative signs gives me a plus, so this becomes C alpha gamma alpha zeta alpha by t, and here in the place of beta raised to the power alpha, since I'm extremely close to Tc, I'm now going to substitute this as beta c. So beta now goes to beta c only after you have taken the derivative, not before that. So that alpha t, C alpha, gamma alpha, zeta alpha divided by beta C alpha. Recall that this C alpha gamma alpha divided by beta C raised to the power alpha times zeta alpha the condition for the condensation to happen at beta C is given by this. So you realize that this quantity that you see over here is nothing but n. So I have alpha n divided by Tc. So here also I have Tc because I have replaced beta by beta C, which effectively also means that I have replaced T by Tc. So del n del T mu being held constant is given by this. So now we have expression for all the partial derivatives we need. We have this value, we have this value, and the quantity that we are looking for is essentially del mu del t times n, which is del n del t mu held constant, del n del mu t held constant with a minus sign in front of it, so that I have del mu del t n held constant is minus del n del t mu held constant divided by del n del mu t held constant, and this is minus alpha n over Tc, and then we go back and look up the expression for del n del mu evaluated at t is equal to Tc plus as this. So I have this, and then I have the expression C alpha minus 1 gamma alpha minus 1 zeta of alpha minus 1 divided by beta C raised to the power alpha minus 1 whole minus 1. So that this is minus alpha n over Tc. And now I want to see, so I have C alpha minus 1 times gamma of alpha minus 1 times zeta of alpha minus 1, and then I have beta C raised to the power alpha minus 1. So let's bring in a KB factor in the numerator and write down this as KB Tc beta C raised to the power alpha minus 1 C alpha minus 1 gamma of alpha minus 1 zeta of alpha minus 1, so that this becomes minus alpha n kb times beta C times beta C raised to the power minus alpha minus 1. Then I have C alpha minus 1 gamma alpha minus 1 zeta of alpha minus 1. Looks complicated, but we are going to simplify this now. Minus alpha, this factor of beta C cancels with the minus 1 factor. So I have n times beta C raised to the power alpha divided by C alpha, and then I have alpha minus 1 gamma of alpha minus 1 zeta of alpha minus 1 1 over this. But go back, and I know that n is C alpha gamma alpha beta C raised to the power alpha times zeta alpha. So let's substitute. So minus alpha C alpha gamma alpha divided times zeta of alpha beta C raised to the power alpha is n. And then I have beta c raised to the power alpha c alpha 1 over alpha minus 1 gamma alpha minus 1 zeta of alpha minus 1. So things cancel out very nicely. C alpha cancels out, except that I have missed out the factor kb, which should have been sitting over here. So I have alpha kb. Beta c cancels out, so that I have minus alpha kb over alpha minus 1, and then I have gamma of alpha divided by gamma alpha minus 1. I have zeta of alpha divided by zeta of alpha minus 1. So this is going to be my del mu del t, n held fixed. Now recall the difference in specific heat we wanted to evaluate, and here we said that this is E. We started off with E as a function of t comma mu, so that dE was del E del t mu held constant times dt plus del E del mu t held constant times d mu. And then we said, look, I am interested in evaluating this derivative del E del t n held constant, so that is going to be del E del t mu held constant plus del E del mu t held constant del mu del t n held constant. And this is the part which I have evaluated. Now I want to figure out, we already have figured out del E del t, del E del mu t held constant, and the difference in the specific heat is just this term is going to be del E del mu t held constant del mu del t n held constant. So we were looking for the term now del mu del t, and we have del E del mu is equal to alpha n. So I have therefore delta c as minus alpha square n kb divided by alpha minus 1. Gamma alpha is alpha minus 1 factorial, and gamma alpha minus 1 is alpha minus 2 factorial, zeta alpha divided by zeta of alpha minus 1. Here we have used the result that del E del mu t held constant was alpha n, so that delta c becomes minus alpha square n kb. Now you immediately see that if you take the ratio alpha minus 1 factorial divided by alpha minus 2 factorial, and this ratio is nothing but alpha minus 1, so that this alpha minus 1 is going to cancel with the denominator, and then I have zeta alpha divided by zeta of alpha minus 1. So things looks very nice, and I have minus alpha square n kb times zeta alpha divided by zeta alpha minus 1, so that the difference, the discontinuity in specific heat is delta c, we write down in a non-dimensional way, is going to be minus alpha square zeta alpha divided by zeta of alpha minus 1. So once I have this, looks is minus alpha square zeta of alpha zeta of, so there is something problem with this pen. alpha minus 1. Let's validate. Alpha is equal to 3, and then you realize that delta C over nkb is going to be minus 9 zeta 3 over zeta 2. This is exactly the expression that we got when we looked at a harmonically trapped Bose gas, and this was the difference in the specific heat. For alpha is equal to 3/2, there is no discontinuity. So again, let's reiterate that for alpha greater than 2, specific heat exhibits a discontinuity as a function of temperature. For alpha less than 2, specific heat is continuous across the transition. So if you want to plot C over nkb, and this is your transition temperature, so let's draw a dotted line that essentially marks this, and let's draw the classical result like this, which is alpha. Then we have the result that it must go as T over Tc raised to the power alpha for T less than Tc. That is what we saw, so that it goes all the way up to here. For alpha less than 2, we also saw alpha less than 2, it is continuous. Not only that, the specific heat at high temperatures approaches the line, the classical result C over nkb is equal to alpha from top, not from below. So therefore it is continuous, and therefore we can always write down like this way. In contrast, so let us just say that this is going to be alpha less than 2, and then I can take the case when alpha is, it's a very poor schematics now, so it goes all the way up to here. For alpha greater than 2, again it behaves like this way, but there is a discontinuity, and that discontinuity will somehow come like this way. Across the transition, the specific heat as a function of temperature exhibits a discontinuity, and this is the amount of discontinuity that you get, which is delta C over nkb, and this expression is minus alpha square zeta of alpha divided by zeta of alpha minus 1, where this is your Riemann zeta function.